Teacher, it's my pleasure to introduce Alexandre. That's two. Alex is a biomedical engineer who's completing his PhD on. Excuse me. Sorry. There we go. He's completing his PhD under Dr. Julien Conadat at Polytechnique, Montreal. His research seeks to improve methods for dynamic slice-wise shimming, RF shimming in both 3T and 7T. Alex is the lead developer of the open source Shimming toolbox, which will be discussed today. The Shimming toolbox streamlines the use of these advanced MRI shimming techniques with standard manufacturer supplied gradient coils, as well as custom multi-coil arrays. Improvements in shimming, I guess, will definitely lead to improvements in spinal cord imaging. I think Alex's work has a direct and meaningful impact on spine image quality. So we are excited to start using the Shimming toolbox on our new CMAX system. And thanks for being here, Alex.
Thank you. So yeah, hi, I'm Alex. So I've heard a lot of talk during this workshop about one of the main problems in spinal cord imaging, which is B0 inhomogeneities. So today I'll tell you what we're doing to increase image quality, but also what we can do to make your life easier to use these tools. So as an outline, I'll first start for those who are less familiar with B0 shimming about all the lingo and everything that, from volume shim to slice-wise to real-time and what you can do to improve your image quality with shimming. And then I'll dive into more details about what we're doing to increase image quality and then also make your life easier. So what is shimming or B0 shimming? So the idea is to make the B0 field as homogeneous as possible. Here's an example in the spinal cord where you start from 100 minus 100 hertz in this case to 0 or close to 0, which is the goal. Here's another example in the brain. This is typical where we see quite some big inhomogeneities near the sinuses. And then on the right, you can see after shimming that we get some homogeneous field, and that hopefully leads to better images. So why do we need to shim? Well, in an ideal world, all your spins are at the Larmor frequency. However, that's not the case. Inhomogeneities are present. And that is what we capture when we take a B0 field map. We capture the delta F, in this case, the frequency offset that's directly proportional to these delta B0 inhomogeneities. They come from different sources. Some can be static. So for example, the different susceptibilities of the tissues. The air is a big one that's very different, so that causes some big inhomogeneities. There can also be metal implants that are just really, really bad in your images. But there also can be dynamic sources. So movement is a big one, but also breathing is another big one. So the amount of air in your lungs, for example, is going to change, and that's going to have an impact on the field map that's going to change in time. So that can lead to problems. Okay, so we have B0 inhomogeneities. Why are they problematic? Well, they cause artifacts. So again, here's a field map. And one of the artifacts that it can cause is geometric distortions. So here's an example in the brain where we just, same acquisition, the only thing we changed is the phase encoding direction, and you can see that the brain is either squished or stretched, and that's caused by the B0 inhomogeneities near the sinuses. Another example in the spinal cord where we can see some homogeneous B0 on the left, and then on the right where we can see the distorted spinal cord because of those geometric distortions. Another artifact that we can see, and that's typically in gradient echo images, is signal loss. So if you have some B0 inhomogeneities, they can cause signal loss to increase because of the increased T2 star decay rate. So on the left, you see pretty much nothing, and then if you shim, you can, although not fully recover, but you can get your spinal cord back with a good shim. So we have different options to shim. The first one that you can think of when you shim is, what coil am I going to use to shim? So on the scanner, you have your spherical harmonics. Typically, you have your spherical harmonics if you use your whole bore scanner. We've talked about order 0, order 1, order 2 during this meeting. So what are they? So the order 0 is just typically your bulk frequency that you can change. Order 1 is your linear shim terms, so they're gradients and they vary again linearly within your scanner. But you also have access to the second order shim. So there are 5 of them, and they vary a bit more or somewhat quadratic fashion in the scanner. Some scanner, the 7T ones, have access to some of the third order, but that's pretty rare and controversial topic. Something to note is that the order 0 and first order can be changed quite rapidly, whereas the second order and above change quite slowly. So if you want to change really fast, your shim terms really fast, then you're limited to the order 0 and 1. Other shim coils that you can use are custom shim coils or external shim coils. Those can be either shim only shim coils, or they can be spherical harmonics, or they can have dipole shapes. So you can see a dipole shape at the bottom right there, and I call those coil profiles. So essentially, if you put 1 amp of current, it tells you how the field is gonna be affected by that. So there's shim only, but there's also what we call AC/DC or I-press coil, which Gary mentioned yesterday, which are coils that combine both either transmit, receive, and the shim coil capabilities. So what are different techniques that we can use? So we have volume shim. So this is probably the most, well, it is the most basic shim possible that we can have. That's what your scanner does. So how that works is you acquire a field map, and then you select a region of interest that you want to shim. So that was the green box at the scanner that we saw on Wednesday. Once you've selected that region to optimize, the field is optimized using either the spherical harmonics of the scanner or the multi-coil shims, and then you get one set of coefficient for your whole volume. So to note, this can be done in pretty much any sequence. There's no fancy thing about any of this. So a next approach that we could use is what we call slice-wise shimming. So this is relevant for 2D acquisitions. And the idea is that you compute a shim coefficient, a set of shim coefficient for each slice that you're acquiring. And by doing that, the idea is that since you have a smaller region that you're trying to shim at once, then you expect that every slice is going to have a better shim. So individually, we optimize each slice, and then we get one set of coefficient for each slice. Again, 2D acquisitions. And on the scanner, if you're using the spherical harmonics, again, the second order, because of its high inductance and it's not shielded, you can't really use the second order unless you want to make your acquisition really, really long. Another thing that we can do is real-time shimming. So that's to correct for time-varying effects. So respiration-induced time-varying B0 fluctuations are problematic in the spinal cord and as well as in the brain. And the idea is to associate the respiratory pressure trace of an individual with these B0 magnetic field changes. So we strap the pressure bellows on the patient's chest so we can acquire how the patient breathes, and then what we expect is that the B0 field is going to change with, there's going to be a correlation between the B0 field and the respiratory trace as well. So what we can do is we can compensate for that for both the static variations as well as the time varying variations, and then we can do that either in volume or in slice-wise fashion. So how would that look like at the scanner? Again, you put the pressure bellows and then you acquire a field map really, really fast, and you acquire multiple of them during, for example, 60 seconds or a minute. So what you can do then is you can take, you can graph it, which is what I'm showing there at the bottom. You can graph the pressure according to the field or according to the gradient, let's say, if you're just doing the z gradient, and then you would expect a linear fit. And then by doing that, you can predict when you acquire in a second acquisition. If you have the pressure, then you can predict, oh, how is the field supposed to be right now, and how I can correct for it. So you can do that with the z, but you can also do that with the x, the y gradient, as well as the frequency. So a colleague in our lab did that for so what we call it real-time XYZ shimming. And then if you compare it to the standard volume shim that the scanner can do, we saw some pretty good improvement, and this was in multi-echo gradient echoes at 3T. Yeah. Another thing that we can do, you've heard all about it yesterday, so I won't spend too long on this, which is dual field of view fMRI. Yeah, the idea being that instead of shimming only one region, then you have multiple regions that you're shimming at the same time. And Christine talked all about it yesterday, which was really great. So this was used in a few publications as well. And what I wanted to show as well is Jürgen Finsterbusch, who has something that's quite similar that he developed, and I won't go into all the details. If you want to look into it, I've put the reference at the bottom, but he showed some good improvements as well. All right, so that's awesome. We have many B0 shimming strategies. What we've talked so far is, we have volume shim, we have slice-wise shim, you can do static, you can do real-time, you can have film map-based strategies. There's the coil you can use. You can do spherical harmonics if you're on the scanner. You can have, if you have your own, you're lucky enough, there are custom coils. There's multiple field of view strategies. But there are also other strategies that I haven't talked about that I'll talk a little bit later. But there are signal intensity-based strategies, SMS strategies. And this is all great, but the problem is most vendors only support, spherical harmonics, and they only support volume-wise shimming. So they don't have those advanced strategies that I've talked about. And the strategies that they do have, which is volume shim, are stuck in black boxes. So that's annoying if you want to know what they're doing and how they're doing it. So the software solutions require specific knowledge to implement if you want to do it on your own. Each research group implements its own code, only works for a specific workflow. It reinvents the wheel if you're doing it at different sites, and it's hard to reproduce. So this was the idea behind Shimming Toolbox. The goal was to create this open source software package to perform B0 shimming experiment and research. So there are many features right now. So you can do your B0 field mapping. You can create your shim coil, shim coil basis creation. So that would be for your custom coil if you have one. You can do volume shim, slice-wise shim, real time. We also have signal intensity based method. And we support the scanner coils, the spherical harmonic coils of the scanner for both Siemens, Philips, and GE. And then we're looking into, other vendors if they're interested. We also support custom coils and much more in the ecosystem. So if you're interested in, I've put the link on there. But we have, some documentation to get you started, some examples, so that you can start doing it as easily as possible. As a side note, we also have B1 Plus shimming in there if you're interested in that. And yeah, if you have any questions or if you have any issues, just same thing as a CT, just ask on the forum or ask on GitHub. So how does that work? Let's say you want to use Shimming Toolbox. So you download it on your computer. You go to the console and then you acquire a few scans. You acquire a scan so that you can segment your region of interest. You acquire a field map, and then you acquire a target, what I call a target image. So the target is just so that we know the geometry that you want to shim. Then you transfer your images back on the computer, and you can have either access to a GUI. So we built a GUI in Fossilize, so that you can look at your data and then experiment. But we also have access to the CLI, so you can do it from a bash script so that you can automate everything, and then just one click you can do your whole processing and get your shim data. So yeah, so you can compute your field map, get your mask, you use whatever coil you want, you use whatever technique you want, volume shim, slice-wise, and then you get a text file that you can send back to the scanner and then use that. So if you're just doing, let's say, volume shim, well, what we've done is, let's say you're on Philips, for example, well, we've scaled the coefficients so that they are what you would expect, and you can just type them in the manual adjustment on Philips, for example. Same thing on Siemens, same thing on GE. All right, so that's what some of the things that we can do. So now let's talk about some of the things that we've been doing in the past year, maybe 2 years. Duke's group showed that simply optimizing the field with traditional least squares can be improved with a dedicated penalty term that will penalize signal loss. They showed this in the brain, and our group wanted to see what would happen in the spinal cord. So here's your typical minimization function that you do. You take your B0 field and then you apply your least square minimization on that. However, if you look at the through slice direction, for example, well, you see that it's you're going to see that it's not just the same thing across the whole slice. The spins are going to have some different. They're going to rotate at a different speed. So what you can do if you assume that this B0 inhomogeneity across the slice is linear is that you can compute a signal loss term using these equations. So using a proxy to this signal loss term, which is the gradient in Z, what we can do is to add a penalty term in the optimization that we can scale with a hyperparameter, which we call W in this case. And then what happens here is that if you put W as 0, for example, then you're back to your normal optimization. But if you increase this W parameter, then you're going to penalize signal loss. So your signal dephasing across your slice. So here's the experiment that we did. So here's we acquired dual echo gradient echo field map that we can compute with Shimming toolbox. You acquire an anatomical image that you can compute a mask, and you acquire a baseline, in this case an EPI. And then we used a 15-channel AC/DC coil, the shim, fed all of that to Shimming toolbox, which computed the shim coefficients, and then we bring that back to the scanner, and then we acquired a shim acquisition. So here are some results. So I'm showing here a single slice. So this is the work from Arnaud in our lab, as well as myself. And you can see on the left, which is your baseline. So second order typical on the scanner, what you do, second order volume shim. And then both on the one in the middle is your typical optimization, slice-wise optimization. And then on the right is using signal loss optimization. And what you can see, the field map looks pretty similar in plane between both the typical slice-wise as well as your signal loss slice-wise. But what's really interesting is the signal loss, where we can see that there's quite a bit of signal recovery when we use the signal loss optimization compared to your standard just optimizing the B0 field. So what you're probably thinking is, okay, well, surely I've helped the signal loss, but what I've probably done is increase my distortions because I've added this penalty term that's focusing on signal loss. So here's some result of distortions. So we're changing the phase encoding directions in 2 slices. And what you can see is that there's pretty much no difference between the distortions from when we go from their typical slice-wise shim to the when we use this signal loss penalty term. So this was great to see. All right, moving a little bit forward. So here's what your typical EPI acquisition at 7 Tesla looks like. Some good slices, but we also have some bad slices. So what I'm showing here is an average of 30 volumes for reference. And I've zoomed in on the bottom row. And this is really typical of what we see when we take some EPIs, is that the bottom row and then some of the first row are, so top and bottom slices are, there's quite a bit of signal loss, and we just don't see anything in the spinal cord. So what we did is we used Shimming Toolbox again, similar workflow, do a echo grade and echo field map, acquire an anatomical, and then acquire a baseline EPI. But this time, instead of using a custom coil, we just use the spherical harmonics of the scanner to do a slice-wise linear as well as frequency shim. So we use this, we get our text file, put it on the scanner, and then we used a custom sequence so that we can change these linear and frequency terms in a slice-wise fashion. So here are some sneak peek results of what we're hoping to show at ISMRM. But you can see on the left, so the baseline, and then on the I guess middle at this point is the slice-wise F0 XYZ shim, and you can see quite a bit of signal recovery and then some much better images when we add this slice-wise shim. And then on the right, you can see some TSNR. So what we would expect is a TSNR through increase. So that's exactly what we see. So overall TSNR that increases when going from baseline to slice-wise shim. And on the right, we're just also driving the point across that the TSNR for really each participant, so in this case that's 5, is overall is really increasing. So we didn't do that just for TSNR measurements. We did that in fMRI tasks. So what we were doing is we had the patient do a motor test. So they had a squeeze ball in their hand. They were all right-handed, and then they were squeezing the ball for 20 seconds, and then they would, after 20 seconds, release it for another 20 seconds, and then they repeated that for, I think, 10 times. And then what we're showing here is that using the baseline, so second order shim in blue, you can see much less activation compared to if you use the slice-wise shimming, we can see much more activation. And then on the right, you can see the number of active voxels. So in this case, in 4 out of 5 patients, participants, we saw an improvement. So some limitations about this method is, this is at 7T, so SAR is an issue, always an issue. So this limits the minimum TR. So if we could have, had more slice, for example, or we could have made this experiment a bit shorter, but SAR is an issue. And the field of view is limited, so reduced field of view techniques could help. And then we've talked to Christine a little bit about it yesterday, but we've seen Artifact using Zoomit 2D RF pulses. So if you have some some insights about this, we'd love to talk about it. All right, so here's what I've talked about now is all about field map based methods. So you acquire a field map and then you shim that. But we also have Jürgen Finsterbusch, who developed this Z-shimming approach, where the idea, and before I dive into it, I'm going to say this is a publication from Merve, so that's awesome. Yeah, so the idea behind the method is that you acquire EPIs, and then during your EPI acquisition, you use 21 different Z-shim gradients, and one of each per volume. So the idea is, you acquire a volume, you have this shim value that you've put, and then you can select which one is the best by looking at the signal intensity in the spinal cord. So this is something we've implemented in Shimming Toolbox as well. And this is what you see at the bottom right with all the blue and red figure, where you can select, essentially the volume that was that produces the highest signal intensity. And this is the shim that you would use for that slice. So here are, some TSNR comparisons, and we saw really some great improvement across pretty much all slices when using this method. So why would you use this signal intensity approach? Field map-based methods work well. However, what Jürgen showed, in 2024, is that if you have a through slice B0 inhomogeneity that's linear, then if you just fit that, so what a field map would do, then you get your optimal signal intensity. So this is a really loaded slide, but I'm going to just summarize it. The point is, if you have a linear B0 across your slice, you can fit it and you get your optimal signal intensity. However, if you don't have a linear B0 profile across your slice, then if you just fit your gradient through it, a z gradient through it, then you don't get your maximum signal intensity. And worse than that, it actually changes depending on your TE. So if your TE is different, then your actual best linear fit isn't what you would fit of the B0 profile. So hopefully that makes sense. So what that means essentially is just that there's some room on the table that if you do some signal intensity, if you use Z shimming, compared to using just Z field map based methods, then you could have potentially some improvement. And I've talked with Merve a little bit, and she said, well, it's marginal, maybe this improvement, but point is that there might be something on the table there. So, okay, that's great. Z shimming based on signal intensity can improve my images. Problem is, with field maps approach, we can do, second order terms, first order term, and we're just limited to Z if we do this approach. So what if we want to add, let's say, as a start, the frequency in my optimization? So here's what that would look like if we naively just, acquire 21 different Z shim values, as well as 21 different frequency values. And then if you do your whole thing, you get 441 volumes, which seems a bit unreasonable, right? That's really slow. And then the worst part is, most of these that you've just acquired are, just don't mean anything, right? They don't give any signal. So you're really limited in accuracy from what you've chosen as boundaries for your shim as well as your frequency. So this is why we wanted to do better. And what we've come up with is to use Fire. So Julien talked a little bit about what it is, and what it allows us to do is to put some Python code or Python tools in a Docker container that's going to be running on the scanner, or more precisely on the scanner reconstructor. So how that looks like is what we've done is we've put SCT, we've put Shimming Toolbox and optimization software in there, and the workflow is you start your acquisition. The first volume is going to come in. We're going to say, oh, there's 20 different slices, so we start 20 different optimization, and then each one of those optimization is going to send one shim set of current to the scanner, and it's going to ask the scanner to use these shim values to acquire an image, and then we acquire the image on the scanner. The image gets reconstructed. We send it back to the reconstructor. We calculate the signal intensity in the spinal cord, and then according to that, we can suggest a new shim value. And then this process just runs, and instead of acquiring your 21 by 21 matrix, what we can do is actually an optimization because we have access to the signal intensity in real time. So what is, we start from 441 volumes to, much less than that. So I've written less than 100 because we're, at the beginning of doing this. But what we see is that we mostly converge usually with F and Z in roughly around 30 volumes. So this is really promising, I think. And the great thing as well is that you're not limited in accuracy in what you choose at the beginning. You're really you can converge to something that's much more specific than your step size that you set when you do Z shimming because you have your step size that's limited. So here's what that looks like on the scanner. So Julien showed a slide earlier, but this is SCT that's been run. Then what we've done is we've expanded using SCT create mask. We've expanded the spinal cord. So you can see it, we're just back and forth so that you can see the mask. But then what we do is you just run your scan, and then you can change some values. So I'm just showing here that we're doing F and Z. Objective function is signal intensity. So you can change some parameters on the fly. You click go, and then the optimization just starts. And you can see it here at the bottom. And I don't know if I can stop it. I don't see that I can stop it, but that's totally fine. Point is, you can see it changing, and those images look terrible. Why is that? Well, most of the images you're going to see when you optimize is it's not good. So that's what we're seeing. Just in real time, it's trying to go from something that's bad to something that's better. Yeah, and it's working. So again, we're at the beginning of this. So what you can see on the left, this was a single participant. So you can see on the baseline, again, your typical EPIs that you're used to seeing, where at the bottom it's signal loss is present, a little bit at the top, and in the middle is the signal intensity based F and Z that I've been showing, and you can see some pretty good improvement. We wanted to test about how it compares with traditional field mapping approach, and we're still not there. Field mapping approach in this case did better, but point is, we're starting to look into this, and it's doing some. I think it's promising. Same story here. TSNR results better than the baseline, but still lacking a little bit behind the field mapping, the field map approach. So some limitations in this is that real-time segmentation of the spinal cord is not something that's currently possible. So what we have to do is take a region of interest that's a little bit bigger than the segmentation, and that includes the CSF. Or subjective flow artifacts. That's not particularly great if you have a hyper intensity. So your optimization thinks that this is really your best shim, but what was actually happening is just a flow artifact. Same thing for a hypo intense artifact. Objective function with only signal intensity is not optimal. If it's fine mostly for F and Z. But if you add X and Y, well, how is your optimization going to know if you have a distorted chord or if it's just the signal intensity? So there's some more work to do there. All right, so the elephant in the room, all the methods I've shown are great, but they're slow. If you want to use it, it takes some time. So I've created these tools, but it takes me, it takes an acquisition of your anatomical, it takes a field map. So that's, relatively fast because you typically have an anatomical anyways that you acquire. So it just requires a field map, but you need to export it. You need to, DICOM to Nifty. You need to, make sure you're on the right folder, you're on your terminal, and then you take it back. You have your you need to take your text file, put it at the right spot. So those things takes some time. I've heard, yesterday I think Alexandre was mentioning it takes 30 minutes to shim, which is really unreasonable. Again, for me who's done this, it takes me maybe 7-8 minutes to do the whole thing, like including acquiring, including exporting, including everything. So that's still better, but it's not perfect. So what if we can do better? So here's a little sneak peek of what we're working on, and it's actually putting Shimming Toolbox on the scanner. So what it allows you to do is you acquire your anatomical, and then using Fire again, in the background, it's going to launch SCT, which is going to calculate your mask automatically. So this is what I'm showing here. And then you launch your field mapping pipeline, your field mapping acquisition, and then during the reconstruction, this is what I'm showing here. During the reconstruction is just computes your field map. So you have your field map just automatically. And then you can send it back on the scanner, and that's exactly what I'm showing here. So this is a small region, but this is your field map that's been computed. And then you can launch your target acquisition, and then same thing happens. That after it's been reconstructed, the shimming starts. So this is what I'm showing right here. So this is all in real time, by the way. The field mapping, I've made it fast, but after that, this is all in real time. So if we just look into where the scanner shim is going to be created, I can take it, copy it to where the next sequence expects it, copied it, and then I can start my shim acquisition. So, it took maybe a minute to acquire your anatomical. It took a minute to acquire your field map, and then 3 seconds for your, let's say 15 for your target, and then you have your shimmed acquisition. You have your shim. So it takes now 3 minutes maybe. So this is what we're working on. Hopefully, if you're interested, let us know, and then yeah, we're pretty happy about it. This is on Siemens, but we're looking into Philips as well. Yeah. So conclusion: B0 shimming has a variety of techniques: field map based, signal intensity based, volume wise, slice wise, static, real time, scanner coil, external shim coils. And all these tools are available in Shimming Toolbox and can be used from the scanner, with this little asterisk saying, mostly on Siemens, but we're working with Philips at this point. And then we're hoping for, if GE has something similar to offer. Slice-wise F0 XYZ shimming for fMRI at 7 Tesla showed great results as well. So we're really excited if you're working with fMRI with APIs. I think even at 3T we see some pretty good improvement. So thank you. I'd like to thank the lab members and funding sources.
All right. Great job, Alex. I guess kind of what, for people, sites out there, like what kind of expertise is needed to get Shimming Toolbox working? And do you need someone like Christine on that site working with them, MR physicists, to help getting it up and running?
Yeah, I think if you want to do volume shim, you don't need much. You need your computer, you install it, and then there's a tutorial. You can follow that tutorial. You get your text file, and then you can just bring that to the scanner. So that's, I think, pretty easy. And then if we've done a good job with the website, hopefully you don't even need my input. If you want to do slice-wise shimming, you need a custom sequence so that the shim parameters can be applied, changed for each slice. So that requires a little bit more involved work. And we're happy to we're working with XA60. I think Christine is now, well, your scanner is on XA61. So we're trying to get that sequence running for you guys so that you can use it. So, yeah, talk to us about it, and then we can see how we can help.
Awesome. And then the application side that you showed was functional MRI.
Mm-hmm.
Are there advantages to structural imaging too?
Yeah,
Potentially?
yeah. So definitely, in APIs, it's definitely, the image quality suffers more from B0. So you see that's where you see the most improvement. In anatomical, it can help. It's just you see it less. I think real time, if your if your image takes 4 minutes and then you're breathing, if you see some ghosting, it can help. So real time can help. But yeah, so it doesn't hurt. It's just less noticeable in anatomical images.
And I assume diffusion imaging.
Yes.
Yeah. Awesome.
Thank you so much for the talk. Something that we're doing in our lab at the moment is whole brain echoplanar spectroscopic imaging.
Okay.
And it's really, really hard to get a good shim,
Yeah.
and it's like make or break for the data.
Mm-hmm.
So just following on from the last question, do you think it's this toolbox could be applied to that? And then my second question is, I'm just trying to get my head around the workflow. So you kind of go in with the participant, you acquire the structural and the field map, and then you compute the values for the shim, and then you put them into the scanner, and then acquire the image.
Yeah.
Is that right?
Yeah, I'll repeat it, but yeah. So first question, yes, it can help. What we've seen, in the brain, is that, because you're shimming a bigger region, it's harder to use, the linear shim terms. They vary quite slowly in space. So we've seen more improvement using the custom coils, but it definitely still helps. So the tool can be used for the brain. If you can use BET if you want to segment the brain. SCT if you want to do the spinal cord, but Shimming Toolbox inherently just uses nifty images, so it doesn't matter what part of where you're shimming essentially. So yes, it can be used for MRSI in the brain. And then workflow, I can repeat it, but you take a field mapping acquisition, so whatever works for you, a dual echo field map, 6 echoes, doesn't matter. You compute your field map. Then the point about the anatomical acquisition is you just want to have a region you want to shim. So if you've already acquired something that's good enough for segmentation, you don't need anything else. You just need something that that you can compute where you want to shim. So this is why we had some MP-Rage or T1. And then for Shimming Toolbox to know, in the slice voice faction, for example, to know where I'm going to shim or where are my slices, then what we do is we acquire what I call a target acquisition, where it's just fast and it's just the geometry that's good. That's going to be the same thing as what you're going to shim. So you acquire that. It can be really, really fast. And then you feed all 3 of those with the shim profiles you're using, and you get your text file. And then with that text file, you use it in the shimmed acquisition that you're actually gonna do your data.
Cool. And so all the while, the participant stays still in the scanner. It's all just in one session.
Yes.
Okay. Cool.
Yeah. I'd say that if you're using your custom coil, for example, then that is going to be something that you're going to do in a phantom, but usually, you're using your spherical harmonics, or if you've done that once, you can use it for all of your participants. So this is why if you take 30 minutes, yes, that's long. Your participants in there, we've brought it down to 7 or 8 minutes if you're using your own computer. And this is why I think that's great, that if we're going on the scanner, then it takes essentially 0 wait time. You just acquire your images.
Awesome. Thank you so much.
Maybe just one clarification is that the full sequence needs to be modified as well in order to be able to ingest that text file.
Gotcha. So you can't just take the like X, Y, Z values from the text file and then put them into the manual adjustment?
You can do that manually.
If you do, yeah, if you do a volume shim, yes.
Yeah.
If you do a slice-wise shim, then the sequence needs to be modified.
Okay, cool. Thank you.
But yeah, it would be better though, as James is mentioning, to do it automatically.
Yeah.
So you don't have to write it yourself.
Yeah.
Thank you for the presentation. It was really nice. I have a couple of questions. So regarding volume shimming, I was just wondering, is volume shimming more effective in any particular direction? I mean, if you do volume shim, does it helps better for the sagittal images or versus the transverse images? Any distinction does it do in that way? And the other thing is that you explained the shimming process really nicely. I was wondering how does it differ, or how are your results for corticospinal shimming, where you have a larger FOV to cover and things like that, compared to only brain or spine? Have you seen any differences for combining the brain and the spine together in your shimming results? And regarding you also mentioned that you are working on Philips, and since we are also working on Philips, it will be really nice to talk to each other regarding how you can implement it in Philips scanner also.
Okay. So first question was, is there a different, have I seen different results depending on their orientation? No.
Volume shimming.
For volume shim, no. So maybe let's clarify. Do you mean the shimmed images, or do you mean like the field map acquisition?
The field maps.
Field map. Well, so if you're in the spinal cord, you probably want some like a better resolution in your Z direction. So a sagittal field map, so where your frequency would be along the Z direction, is probably going to help because you have more resolution in the Z direction. So a sagittal field map could be better in this case. Other than that, is there really something different between volume shim and slice-wise shim? I don't think so. Yeah, does that answer the question?
Yeah, like if you acquire for the spinal cord, if you acquire the transverse images, the axial images,
yeah.
In that case, how does the volume shim make sense, or is it? I mean, if my basic question is that does it help in the correction in one direction more than the other in case of volume shimming?
I don't think so. No.
Okay.
No. I remember your third question. Yeah, we should talk. And then your second one was
corticospinal.
Corticospinal, yeah. So we've tried it a little bit. It's definitely hard. And one of the main reason why is I think it's better to use a tool like this than just setting a rectangular volumic shim box that's on the scanner, because you can really segment the brain, segment the spinal cord, and then you're really shimming your region of interest rather than something else. So I think it's better to do that. The only problem is the spinal cord is really small, and then your brain is really big. So you're really focusing your shim on the brain because it's bigger. So this is something Julien was referring to yesterday. So I think it's better to do that than just a volume shim box that's available in the scanner, but that's still challenging for sure.
Okay. And do you think volume-based shimming works better or slice-wise in case of a corticospinal imaging?
I think slice-wise is going to help. Yeah, if you have.
I mean, there is always better results in the slice-wise as you have shown, but considering the time and other things, in case there is a trade-off, right?
There's, I'd say in terms of results, if the shim is doing well, I don't see really even a trade-off. I see slice-wise just performs better.
Better, all the-
Yeah.
Okay, thanks.
Did you get your answer question about Phillips? But except you're going to work together.
Yeah, was a
Got it.
comment.
A comment, not a question.
I have questions about the real-time shimming or compensating the breathing artifacts. Is there any concern about delay?
Yes.
Like, are you like one volume behind the previous one?
So we're not one volume. I mean, so during the shim acquisition, like the sequence is gonna fetch what's the latest PMU, like latest value from the PMU, and there is a delay, but it's really small. It's a few milliseconds.
Okay. And looks like you explained that you have measurement first, and then you applied it. Does the calculation limited to the range of breathing during the calibration part? In other words, if people are breathing
Erratically,
normally and then all of a sudden they take a deep breath, would that be a problem?
Yes, we typically ask the participant to breathe normally throughout the acquisition and not change it. But yes, that's something to think about. It would in the Siemens world, it would clip if they decided to do a big acquisition, a big inspiration or expiration. So it would clip, and that's not great because there's some processing on there, and it's a bit annoying. But point is, yes, it would it would hurt a little bit, but it would clip. So essentially, we just wouldn't have the best shim possible, but I would expect it to still be an improvement because we're still, let's say, inspiring. Does that makes sense? So it's just expiring more, but it's going to help, but not as much as if we had captured the whole thing. Does that make sense?
Yeah. I guess my question is the dynamic range within the calibration has to be bigger than the actual dynamic range of the breathing? In other words, if you breathe more, inhale bigger than when you calibrate, would that be a problem?
It would be a problem in the sense that we wouldn't shim optimally.
Okay.
Yes.
Yes. Follow-up comment. Could you have, within that training period, breathe in deeply, exhale all the way, like that, instructions like that maybe could help with the training.
Yeah.
Maybe it's part of it.
Well, it's not. So great suggestion. So it could. The only thing, and we're trying to remove that processing from the bellows, but the problem is there's a recalibration process going on with the bellows. So if you go like really deep and then expire really deep as well, it's gonna come back to the same range, and then when you shim and then you're just breathing normally, it's going to have the same range, but you were inspiring and expiring more deeply. So
Okay.
yeah, there's
So
an issue there.
training could be don't ever take a deep breath.
Yes.
Don't exhale all the way.
Yeah.
Stay in this middle range.
Or don't breathe
That
at
could
all.
be
Yes.
I recently learned of liquid ventilation, and they can maybe I don't know if it really works. Fill the lungs with fluid that has like a lot of oxygen in it, and that could also help with the shimming issues.
You might try that.
Yeah, I know. Yeah, you could look it up. I don't know. It's sci-fi. Question is, how long is the training period for this?
I think we were 60 volumes, so depending on the number of slices you have, 90 seconds, 2 minutes.
Additional questions?
So we have big problems with field inhomogeneities caused by the implants. which prevents us from doing diffusion, fMRI, gradient echo sequences close to the implants, right? So do you think it's hopeless to correct for those inhomogeneities caused by the lesion, these severe artifacts, or there is a hope?
So are you saying your inhomogeneities are really, tiny but big? Is that what you're saying? Like
Yes.
they come from.
Yeah.
Yeah.
So basically, at where the implant is, you just see dropout. At the edge of the implant, you see the distortions, but the distance where it goes from really bad to really good is very short.
Yeah.
Yeah.
Well, if you use, your linear shims, then this is really, you have you're spatially varying really slowly.
Yeah.
So that's going to be hard. I think maybe some, custom coils, so where the field is spatially varying more rapidly, that could help. But implants are hard. So I think it could help, but I don't know how much. I haven't delved into that field, let's say.
Thanks.
No. Okay.
Just have a comment. So something I really like the real-time segmentation. I think it is already feasible for cardiology. I've definitely seen Dan Ennis's group use the SEMA X to segment blood vessels by drawing a line through them. So I think maybe it would be nice to look at other fields and see like how they're adapting in case you run into issues.
Sure.
And also like maybe how different scanners and software versions could work. So awesome.
Thanks for the comment.
Yeah, and also like other applications outside of spinal cord.
Sure.
Like I'm sure there are, right?
Yeah.
We're interested in this. Yeah, not be the best question, but we're interested also in being able to look at post-surgical changes and people with hardware. Could this help with that, this shimming, to be able to better image around metal?
I think I have the exact same answer as the implants, right? Yes, but to what extent is it really going to help? It's going to help, but I don't know how much. I don't know. I think using the spherical harmonics of the scanner that's slowly varying, that's going to be really hard because the inhomogeneities are quite small, but strong. So custom coil might do better. I just don't know how much.
Great talk, Alex. So just few comments about the nomad optimization approach. You were mentioning that adding the X and Y would take additional time. So I was just wondering if maybe we could consider an approach where we would use the field map to estimate the X and Y, and the nomad optimization to get the GZ and the F0. Maybe something to think about.
Yeah.
Also, maybe as something to brainstorm with all the community here is that Alex has been presenting real time with the signal from the bellow, and then we clearly highlighted the limitations of the bellow, including the clipping and the processing done under the hood by Siemens. And so I'm really interested in looking at Navigator as a surrogate for breathing pattern. So that's something we might want to investigate as well.